So hi, I'm Gabor Angeli, and I'm going to be talking about NaturalLI, a system for inferring common sense facts or world knowledge. So it's very fitting. What do I mean by common sense reasoning? I mean, we'd like to know that, shorts are not a toy and marbles are toys, or kittens play with yarn and computers don't usually, kittens don't play with computers, usually. Or, more relevant for NLP, if we have something like the Winograd schema for coreference, the city refused the demonstrators a permit because they feared violence. Well, we'd like to know that a city fears violence and demonstrators generally don't fear violence as much, so therefore they is probably the city. For something like PP attachment ambiguity, I ate the cake with a cherry versus I ate the cake with a fork, we'd like to know that cakes come with cherries and are not eaten with cherries. Or, there's cute examples in things like humor, sarcasm. Put a sarcastic comment in your talk. That's a great idea. Well, if you know that sarcasm is not a great idea to talk, you can recognize that this is a sarcastic comment. And another part of NLP should be helping the other areas of AI. So for example, vision, it just seems clear that if you have a car, you know it's a car, and you're trying to recognize who's inside of it, then it's probably a person, probably not a dog. Or, if you have a baseball player and you know it's a baseball player, then the thing under it is probably grass and not water, and so forth. So, of course, this is not a new task. I mean, it goes back to, I guess, what I call old school AI. And really, the older work in this I characterize as sort of very nuanced reasoning, but generally tiny coverage. So probably less useful in nowadays applications. I guess maybe more recent vein is textual entailment. Like really the RTE challenges, and I put episodic logic in here too, are sort of trying to capture very rich inferences, but still tend to operate on relatively small or limited domains or data sets. And on the opposite extreme, I put information extraction. Things like OpenIE and NEL are trying to extract these gigantic corpora of facts, either factoids or common sense facts, but the inference is, well, quote unquote shallow. Usually it's just direct lookup or sort of relatively shallow inferences, if there are. So we're actually going to start from the OpenIE side of things, or the information extraction side of things. We start with a large knowledge base of things like the cat ate a mouse, all cats have tails, all kittens are cute, so forth. And what we'd like to do is infer new facts. So sort of the outline of the talk is knowledge base. Conceptually, we want to infer new facts, either their truth or falsehood, like no carnivores eat animals is false. But we don't want to run inference over every fact because it's a very large knowledge base. And we don't really want to store all the results because every fact can infer a whole bunch of other stuff that we don't have space to store. And so we're going to flip it around. We're going to say we have our large knowledge base, we have a query, and we're going to find either support for or for the negation of the query in our knowledge base. Furthermore, we're going to do this trying to use text both as the representation for the knowledge base and for the inference, because we have lots of text and it's much harder to translate into something like first order logic. And we want to do it without aligning to any particular premise. And in part, this is, I think, just aesthetically clean, but in part it carries advantages like you don't have to have lexical similarity between your premise in the knowledge base and the query. So no carnivores eat animals and the cat ate a mouse actually have very little lexical overlap, but nonetheless one negates the other. All right, so this whole line of work is useless if no one uses it, so this is my sales pitch. If you're trying to look up things in knowledge base, then at minimum we're going to be better than just vanilla lookup. So previewing the results, if you have a 270 million entry knowledge base and you try and look up by just the lemmatized query, then you get around 12% recall. And with NaturalLI, with our system, you bump that up to 49% recall at 90.6% precision. And furthermore, you can always improve recall by making the query more and more fuzzy, but we'll do more than that. We'll give you a notion, at least try and give you a notion of formal logical entailment rather than just similarity. And at the same time, we hope to maintain the good properties of just fuzzy lookup We try and be fast during inference. We have minimal pre-processing of the query and really no pre-processing of the knowledge base. So what's the secret sauce? Well, natural logic. So hopefully we've motivated why we want to do common sense reasoning. I've given a brief outline of what I'm going to talk about. And the next step is to introduce natural logic. If you don't want to hear about it, or you're zoned out, or you will zone out soon, then you can just replace natural logic with syllogistic reasoning for the rest of the talk, and you'll get more or less the gist of what's going on. So if we have something like some cat ate a mouse, and we know from WordNet that all mice are rodents, then some cat ate a mouse entails that some cat ate a rodent. And it's important to note here that even with these very simple patterns, we can already do things that are cognitively easy and yet very hard in first-order logic. So if we have most cats eat mice entails most cats eat rodents, this is a very trivial inference, but actually not computable even in first-order logic. To give a more real-world example, if we know that all students who know a foreign language learned it at university, then it's actually rather hard to come up with a first-order logic parse of that sentence, but it's both cognitively and for natural logic very easy to infer that therefore they learned a foreign language at school. All right, so the high-level takeaway here is that facts in natural logic are just text, and inference is going to be lexical mutation on this text. All right, so I'm going to drop into an example soon, but before that we need to introduce polarity. If we take hypernymy as this sort of partial order, this lattice where animal is greater than feline is greater than cat, greater than just means superset of the denotation, then the polarity of a lexical item is the direction you can move in this lattice. So if we represent that the lattice is just a simple order, animal greater than animal greater than feline greater than cat, then if something is upward polarity or has upward polarity, you can move up to feline and animal. And if it has downward polarity, you can go down from animal to feline to cat. All right, so let's take an example fact. All cats eat mice. The quantifier all in this case determines the polarity of the arguments. So cats is down, eat, and mice is up. And we can start mutating. So all cats eat mice entails that all house cats eat mice. Entails that all house cats consume mice. But doesn't entail, so all house cats consume mice, doesn't entail that all house cats consume field mice. They might be consuming house mice, or whatever other kinds of mice that there are. So we have to go the direction of polarity. And it's also important to note here that inference is reversible, with some caveats for which you'll have to look at the paper. So going back, why are we using natural logic? Well, it's computationally fast during inference. The query doesn't need to be pre-processed, and the inference itself is just simple lexical mutations. It's computational fast during pre-processing, namely there is none. The knowledge base is just a bunch of text. And it still captures many valid inferences. So there's no free lunch. We haven't solved first-order logic, reasoning, theorem proving. It's less expressive than first-order logic. But nonetheless, many of the things that we think are just very trivially intuitive, it will capture. And this is in particular important because these are the kinds of inferences that we expect readers to make instantly and effortlessly, and therefore these are the kind of inferences that I think that we write regularly, expecting our readers to understand. All right, so I've talked, that's all I'm going to say about theoretical natural logic, I guess. We've talked about inference, and the next part is going to be to cast it as search. So now we're going to be in the query look for support paradigm, and we're going to start talking about search. So what does a search problem look like? This is my caricature of search. Well, we have to define the nodes. The nodes in this case are going to be a fact, and whether or not the truth is maintained for that fact. So for example, the start node is the query fact, and of course the query fact entails the query fact. The end node is going to be any fact in our knowledge base. The edges then are going to be mutations of the current fact, and we hope that this will follow, roughly logical entailment, and we enforce that by the edge costs, which is how quote-unquote wrong the entailment is, which will be learned, and we'll get to that, well, I guess kind of get to that later. All right, so now I'm going to go through an example search. The only complicated thing here is now our polarity is reversed. So if something has downward polarity, rather than going down, we're going up because it's a reverse inference. And we can then take our start node, no carnivores eat animals, and maybe start searching in some direction. Let's say we replace no with the. This will negate the truth. So what is it? No carnivores eat animals entails that it's not the case that the carnivores eat animals. And we might go from carnivores to felines, and then to cats, and then animals to chordates. And I won't go all the way down, but that eventually does get to mice. And maybe we'll insert an in there, and this is an end node. And now our search is done. So to make it look more search-like, let's collapse our search state, which is this fact with the polarity markings, into just a plain text. Textual node, I guess. And now we can see our search more conventionally as a graph search. We start with no carnivores eat animals. It has a bunch of options of where it will search to, maybe the carnivores eat animals, or no cats eat animals, or various other options. Let's say it takes the first one. The carnivores eat animals. Now it can go to the feline eats animals, all carnivores eat animals. And in this way, we search down until we hit our end node, the cat ate a mouse. We recognize that this is in our knowledge base, and we're done. The last thing I want to talk about is the edges. So if we go back to our start node, no carnivores eat animals, to the carnivores eat animals, then what we're really doing from a natural logic perspective is we're negating the operator no to be the, which is an operator negation. In particular, the instance of the template operator negation is going to be we're negating no to be the, and there's a particular edge, no carnivores eat animals, to the carnivores eat animals. And in a sense, it's clear that we need some sort of hierarchy on the edges, because an edge in our graph is just a mutation of any string to any other string, and we can't store that even plausibly. So the instances kind of define what the graph should be. We can now generate this graph on demand, and the templates are going to be the things that we define weights over, in a sense. So this is the various natural logic operations. In particular, the list is here. There's at the top the four word net relations that we use: hypernymy, hyponymy, antonym, synonym. We can add and remove words. And then there's the four, operator operations, which are, interestingly, there's a neat fact that they're actually just the directly analogous to the word net relations. And then we have some fuzzy relations like nearest neighbors edges to capture fuzzy entailment. On which note, really what we want is not just, whether or not it's strictly formally valid, because that's actually even kind of not well defined for language. We want some notion of soft entailment, and we want this for the same reason we have Markov logic and probabilistic soft logic and all these other soft versions of first order logic. And it turns out it's super simple to do. We just say that each of our edge templates, like operator negation or hypernymy or so forth, has some cost, which has to be greater than or equal to 0 just for the search to work. Furthermore, there's a detail here that each instance, like going from cat to feline or cup to container, we want to have actually somewhat different distances. Cat to feline should be small, cup to container may be bigger. Nearest neighbors has their actual distance that we want to encode. So each edge instance also has a distance f. And then the cost of an edge is just multiplying these two together, which means the cost of a path is just the sum of all the costs of the edges. And of course, we can and do learn these parameters theta, which I'm not going to go into in the presentation, but it's in the paper if you're interested. It's not particularly exciting. So the last contribution I want to go over is what I call simple transitivity. So through the whole talk, I've kind of assumed that if A entails B and B entails C, then A entails C. Seems obvious enough. But it turns out it's actually a bit more complicated in at least prior work on natural logic. So if we want to determine all bats are nocturnal, does that entail or not entail not all bats are diurnal, daytime dwellers, I guess, then it's clear that there are two mutations, nocturnal to diurnal, which is in this weird, funky vertical bar relation, which is a lot like negation, but notice you can have things that are neither nocturnal or diurnal, trees. And then all to not all, which is just straightforward negation. And it turns out there's a table to solve this. So if you go down on the left, that weird vertical bar, and go over to the right to the weird hat thing, then you get this weird subset thing, and that weird subset thing means entailment, and the system works. But it turns out you can do this much simpler. So you can by and large ignore much of this table, or at least simplify it to a simple binary distinction of whether it's entailed or not entailed. So all bats are nocturnal, entails itself. If we have the mutation, nocturnal is in this weird relation with diurnal, then this will then entail a negation of it. And we don't have to care which particular relation is in there, just that it's now negated. And now if we negate it again with this funky hat relation, we don't have to care what relation this negated fact was in, we just negate it again. And so the complex join table from the previous slide can just be reduced to tracking the simple binary distinction, which makes search much easier and it makes the whole framework much easier to use. So hopefully we've motivated common sense reasoning. We've talked about natural logic. We've talked about the search mechanism by which we do inference. Onto experiments. We have 2 experiments. The first one is on the Fracas textual entailment suite, which is the same thing used by McCartney and Manning, 2007, 2008, the prior work on natural logic. And these are roughly RTE-style problems. So, at least 3 commissioners spend a lot of time at home entails at least 3 commissioners spend time at home. If we change at least to at most, then at most 10 commissioners spend a lot of time at home doesn't entail that at most 10 commissioners spend time at home. So they look a lot like this. There's 9 focused sections, each testing some specific phenomena. Of those, 3 are in scope for this work, and it's the same 3 that are in scope for McCartney and Manning 2007. So roughly the ones that are supposed to be captured by natural logic. And it's important to note here that this is not a blind test set. Both for McCartney and for us, this was sort of the, dev set in the human development sense of the word. Can we get natural logic to work? For us, what we want to test is, can we make the sorts of deep inferences that McCartney and Manning could make, knowing the premise and just having to align the premise and the conclusion, where in our case, all we have is the query, and we're searching for a premise blindly, and can we still recover the inference that we want to? And the conclusion, so here are the 3 systems, MO7, MO8, and N, which is us. And it turns out that for quantifiers, we're basically the same. Adjectives, we do a little worse. Comparatives, we do a little better. And all in all, it's a wash compared to McCartney 08. Across the board, we do better than McCartney 07. So yes, we can still capture formal natural logic despite not knowing the premise a priori and just searching more or less blindly. The other experiment, which is really the real experiment, so to speak, is going to be inferring common sense facts. Our source of common sense facts is going to be concept net. So things like not all birds can fly, noses are used to smell, nobody wants to die, music is used for pleasure. The negatives are going to be reverb extractions marked false by Turkers. So presumably facts that are plausibly correct but aren't. And even though this is relatively small, so it's only around 1,000 test examples, it's broad coverage in terms of the domain of things asked. And the knowledge base we use is going to be 270 million lemmatized OLI extractions, just flattened out to be plain text. So the 2 systems I want to compare are just direct lookup. That is, we have 270 million extractions. It's not unreasonable to expect that stripping away trivial lexical variation, you'll hit a lot of stuff. And then NaturalLI, which is our system. And a third, for, completeness, a third system, which is naturally ignoring direct lookup. So this is only using inference and not allowing the trivial step of, well, let's do a search and we hit the end node. So direct lookup, precision is 100, never makes a mistake. But recall is only around 12%. So only around 12% of the facts have any support in the knowledge base. If you use NaturalLI, you go up to around 49% recall, maintaining around 90.6% precision. So we roughly quadruple the recall. And we maintain much of that using only inference. So in conclusions, the takeaways that I'm hoping you're taking away from this, we do deep inferences over a large knowledge base. The knowledge base can just be plain text. You don't have to parse it with a semantic parser or anything else. Even with a syntactic parser for that matter. And we have a soft logic that'll give a probability of truth. The sales pitch is it's strictly better than querying a knowledge base. If you want common sense knowledge and you've been using, OLI or NEL or something, then you should plug this guy in and your recall will go up. And it'll check logical entailment and not just a fuzzy query of similarity. And lastly, the complexity, the knowledge base can grow to arbitrary sizes, basically anything that fits into memory on your machine, and the complexity of inference won't go up. That is the runtime complexity. And thanks. That is hopefully a demo, which will hopefully work if you guys want to try it out. And that's all I have.
Very interesting, thank you. I thought I saw briefly on slide 13 that there was an example with two quantifiers. Once you have multiple quantifiers, you can order them in different ways. So is that just handled in your weight vector, or how do you, maybe it was somewhere around here.
It's somewhere in there.
Yeah. So what do you do with multiple quantifiers?
So the syntactic parse gives you the nesting of which ones should be nested. From there, we try and determine the two arguments of it via a set of actually just deterministic rules, the same ones used by McCartney and Manning. Mm-hmm. And natural logic does give a calculus of how you propagate the information from each quantifier through each other. So this is one of the things that's different from syllogisms. I say you can just replace it with syllogisms, but in fact, we do handle multiple quantifiers in arbitrary text. The paper has much more.
I was wondering, I don't know if you showed that, but what do you use as a search method? Like you showed your cost function, but do you use best first search or?
Uniform cost search.
Uniform?
So, yeah, I guess simple Dijkstra's.
Thanks, Gabor, for the nice talk. So one of my question is, do you want to, incorporate more variations of search strategies in your search? Syntactic features or syntactic structure or other types of more variations. I'm a little bit worried about the search stuff. You do the mutations, not too many examples there.
We can insert and delete words and modify quantifiers, and in principle, the search should be completely connected. So you should be able to get from any sentence to any other sentence. You're right that, on the other hand, that adding and removing single words is not the most principled thing to do, and we know about this, and we're working on it. And in fact, there's already a version that runs on parse trees, where you add and remove constituents I guess still constituents in a dependency tree. Thank you.